Vortices are most noticeable when the aircraft is low and slow, like in a landing configuration. With this quartering tailwind, look what happens. These wingtip vortices travel from 1/8 left, right across onto 1/8 right. And if you are landing on this runway in a small airplane, this can be a potentially hazardous condition. So the question is, how the heck do you avoid wingtip vortices? Well, here's what you do. Here's your small airplane right here. The idea is to watch that larger airplane ahead of you and keep ahead, right, or keep higher than the descent rate of that larger airplane. So you want to land ahead of that airplane right here, see? And then if you are rotating out to take off, the idea is to get out and climb ahead again or before the rotation of these wingtip vortices. So on touchdown, land after that wake or ahead of that aircraft, the larger aircraft ahead of you, and on takeoff, climb out before or ahead of that larger aircraft or before those wingtip vortices begin. Here's an FAA test question for you right now. When landing behind a large aircraft, the pilot should avoid wake turbulence by staying A, above the large aircraft on final approach path and landing beyond the large aircraft's touchdown point. B, below the large aircraft's final approach path and landing before the large aircraft's touchdown point. Or C, above the large aircraft's final approach path and landing before the large aircraft's touchdown point. I think we just covered this, and I think your answer should be A. Don't forget to avoid wake turbulence caused by wingtip vortices. A, land above that large aircraft's final approach path and landing beyond the large aircraft's touchdown point. That's how you avoid wingtip vortices. Let's move on, talk about P factor. Here we have our airplane, straight and level flight and in a climbing situation. And here we have the propeller. And once again, don't forget, the propeller is nothing more than a moving or a spinning wing. So we also have a relative wing to deal with. And we have right here, this is the angle of attack of our propeller. Now, in a straight and level situation, the amount of thrust being generated by the ascending and the descending blade is going to be equal. And as you sit in the cockpit and that propeller turns around, it turns in a clockwise rotation. So the descending blade is going to be on the right-hand side. All right, now you put the airplane into a climb right here. Look what happens. Our angle of attack has obviously changed. What's going on right here, the descending blade on the right-hand side is now generating more thrust than the one on the ascending or left-hand side of the airplane, and that has a tendency to yaw the airplane off to the left. All right, we'll move on. Left turning tendency. Remember Sir Isaac Newton and his third law? For every action, in this case, the action of the propeller turning to the right, we're going to generate an opposite and equal reaction. And that is going to be this, a roll to the left. The forces counteract each other. Here's our final concept in this, and that's going to be slipstream reaction. Now, as the propeller turns, it generates air moving over the wings and down the fuselage. That is a slipstream. Now, as this air strikes right here, the backhand or the left-hand side of our vertical stabilizer, it's going to do what? It's going to have a tendency to yaw that airplane off to the left and roll it off towards the right. The good news here is it's pretty easy to fix this problem by simply designing the vertical stabilizer in such a way to minimize this effect. Time right now for an FAA test question. The left turning tendency of an airplane caused by P factor is a result of the A, clockwise rotation of the engine and the propeller, turning the airplane counterclockwise, or B, the propeller blade descending on the right, producing more thrust than the ascending blade on the left. Perhaps C, gyroscopic forces applied to the rotating propeller blades acting 90 degrees in advance of the point the force was applied. Well, I think we can eliminate one of those already. Your answer should be B, propeller blade descending on the right, producing more thrust than the ascending blade on the left. People, this is not rocket science. Here's our final concept to talk about, and that's going to be ground effect. Now, ground effect occurs when the aircraft is less than one wingspan above the ground, okay? Here's what ground effect is. When an airplane operates less than one wingspan above the runway surface, that surface interferes with the airflow being generated by the wing, reducing the wingtip vortices. As a result, this actually improves the aircraft's aerodynamic performance, okay? Now, this improvement is primarily caused by a reduction in induced drag. This phenomenon is called ground effect. As a consequence, any excess speed in landing causes the airplane to float down the runway. That means if you come in for a landing and you are carrying too much speed on final approach, as you get down closer to the runway and you get less than one wingspan above the runway, your induced drag is decreasing, your wing performance is increasing, and the airplane has a tendency to float down past your landing spot. Not a good thing to have occurring if you're landing on a short runway. You could be eating a chain link fence real fast. Now, the opposite is also true on takeoff. On takeoff, ground effect can also cause an airplane to become airborne before reaching its recommended takeoff speed. So you can get the airplane in the ground above its recommended takeoff speed, but as soon as you climb out of ground effect, you lose that benefit and you lose the lift. Here's an FAA test question for you right now. Ground effect is most likely the result of which problem? A, settling to the surface abruptly before landing. B, becoming airborne before reaching recommended takeoff speed. Or C, inability to get airborne even though airspeed is sufficient for normal takeoff needs. Hey, your answer? It's B. Remember, becoming airborne before reaching the takeoff speed. Well, we covered lift, thrust, drag, and gravity and figured out what keeps an airplane in the air. Now it's time to move on to another lesson, but first, here's Matt.
As you can see, aerodynamics is perhaps the most interesting lesson. Okay, now it's time to open your workbook or start your computer and complete all the questions selected for this lesson. Now when you've completed at least 80% or better, start the next lesson.